Welcome to Chapter 5, where we explore hybrid approaches that integrate composition-based and GNN structure-based features. In Chapter 4, we saw that each approach has distinct strengths. Composition features are data efficient, while GNN features capture structural information. Now we'll learn how to combine them to get the best of both worlds. By the end of this chapter, you'll understand the design principles of hybrid features. Implement and evaluate ALIGNN, which uses line graphs to capture bond angles. Implement MagNet for simultaneous multi-property prediction. Compare early fusion versus late fusion integration strategies, and evaluate the practicality and limitations of hybrid models. Let's start with the fundamental design principles of hybrid features. The core idea is to effectively integrate features obtained from different information sources. Composition-based and GNN features contain complementary information. Composition features operate at the element level with statistics like mean and variance, while GNN features work at the atom level with position and bond information. Composition features work well with small datasets under 10,000 samples, while GNN needs larger datasets above 50,000. The hybrid approach aims to combine multi-scale representation, balanced efficiency and accuracy, and multifaceted interpretation capabilities. There are three main strategies for feature integration. Early fusion performs feature-level integration, concatenating composition features and GNN embeddings to learn with a single model. Late fusion performs prediction-level integration, combining predictions from independently trained models. Intermediate fusion, used in architectures like ALIGNN and MagNet, integrates different representations at intermediate layers of neural networks. Mathematically, early fusion concatenates the feature vectors. H hybrid equals the concatenation of H composition and H GNN. Late fusion combines predictions with a weighted average. Y hat equals alpha times YRF plus 1 minus alpha times YCGCNN. The optimal alpha is determined through validation, typically giving more weight to the better performing model. Let's dive into early fusion, the simplest hybrid method that directly concatenates composition features and GNN embeddings. In early fusion, we concatenate MagPi's composition features with the GNN's embeddings, creating a combined hybrid feature vector. This combined vector passes through fully connected layers for prediction. The implementation is straightforward. The GNN computes graph-level embeddings through convolution and pooling, then we simply concatenate with pre-computed composition features before the final prediction layers. Early fusion shows impressive performance gains. On mapbench formation energy prediction, random forest with MagPi achieves good baseline performance. CGCNN alone achieves better results. Hybrid early fusion achieves the best performance, showing meaningful improvement over random forest and improvement over CGCNN alone. The R-squared also improves with the hybrid approach. Early fusion has several advantages. The accuracy improvement over CGCNN alone is meaningful. Composition information assists GNN learning, improving data efficiency, especially for medium-scale datasets. The implementation is simple and easily integrates into existing GNN architectures. However, the increased feature space raises overfitting risk, requiring dropout or regularization. Different feature scales may need normalization. Now let's examine late fusion, which takes a different approach by combining predictions from independently trained models. Late fusion trains random forest and CGCNN completely independently, then integrates them at the prediction stage. The ensemble prediction is computed as a weighted average of each model's output. The optimal weight alpha is determined by searching over values from 0 to 1 on validation data, finding the combination that minimizes MAE. Late fusion results show that the optimal weight gives majority weight to CGCNN and minority weight to random forest prediction. This makes sense since CGCNN has better individual performance. The ensemble achieves improved performance, better than random forest alone and better than CGCNN alone. The method provides stable predictions through model diversity. Comparing early and late fusion reveals interesting trade-offs. Early fusion achieves better accuracy. However, late fusion offers advantages. It uses existing models without retraining, provides stability through ensemble diversity, and allows fallback if one model fails. Choose early fusion for maximum accuracy and late fusion for stability and ease of integration. Now let's explore ALIGNN, the atomistic line graph neural network, which represents the state-of-the-art in materials property prediction. ALIGNN uses a dual graph approach with both atom graphs and line graphs. The crystal structure is converted into an atom graph, where atoms are nodes and bonds are edges, and simultaneously into a line graph, where bonds become nodes and bond angles become edges. Separate convolutions process each graph, then an interaction layer combines their representations. This explicitly captures bond angle information that standard GNNs miss. The distinction between atom graphs and line graphs is crucial. In an atom graph, nodes represent atoms and edges represent bonds between atoms. In a line graph, nodes represent bonds and edges connect bonds that share an atom, encoding the bond angle. For example, water has 3 atom nodes and 2 bonds in the atom graph. In the line graph, those 2 bonds become 2 nodes, joined by a single edge that encodes the HOH angle. ALIGNN performance is impressive. Standard CGCNN achieves good baseline performance. A simplified ALIGNN with just improved message passing achieves somewhat better results. The full ALIGNN implementation with line graphs achieves excellent predictive performance, showing meaningful improvement over CGCNN. This represents state-of-the-art performance on many MapBench tasks. ALIGNN's advantages include explicit bond angle modeling, which is crucial for distinguishing polymorphs and capturing directional bonding. It achieves state-of-the-art performance. However, line graph construction increases computational cost compared to CGCNN. The implementation is complex and harder to debug. With small datasets, the increased model complexity raises overfitting risk. Let's now examine MagNet, which takes a different hybrid approach through multitask learning. Multitask learning simultaneously predicts multiple properties using shared representations. The total loss is a weighted sum of individual task losses. This approach improves data efficiency since correlations between tasks provide additional training signal. It also improves generalization by leveraging cross-task patterns. The key challenge is setting appropriate task weights lambda k to balance different loss scales. MagNet's architecture consists of shared GNN layers that compute common graph embeddings, followed by task-specific prediction heads. The atom embedding and the shared graph network convolutions are common to all tasks, learning general material representations. One caveat: the reference MagNet architecture updates a global state vector alongside the edges and nodes rather than using attention, so treat what we build here as a MEG-net-style teaching simplification. Each property, like formation energy or band gap, has its own final prediction layers. This shared then-specific structure enables efficient parameter use while maintaining task-specific flexibility. MagNet multitask results show promising data efficiency. For formation energy, the multitask model achieves performance comparable to single-task CGCNN. For band gap, performance is also competitive with single-task approaches. The key benefit is that a single model predicts multiple properties with shared computation, effectively doubling data utilization. Multitask learning faces several challenges. Negative transfer occurs when task correlations are low, causing performance degradation compared to single-task models. Task weight tuning is difficult since formation energy and band gap have different scales. A naive equal weighting would let the larger scale loss dominate training. Solutions include task clustering for correlated properties, uncertainty weighting that automatically adjusts task weights, and separate task-specific layers. Let's now comprehensively compare all the hybrid methods we've explored. The comprehensive comparison on MapBench formation energy shows clear patterns. Random forest magpie achieves the baseline performance. CGCNN achieves better results. The simplified ALIGNN improves a little on CGCNN, late fusion improves a little further, and early fusion further still. Full ALIGNN achieves the best results of all. MegNet multitask achieves performance comparable to CGCNN while providing multi-property prediction capability. The accuracy versus training time trade-off reveals important practical considerations. Random forest is extremely fast but less accurate. CGCNN takes moderate time with good accuracy. Early fusion and late fusion have similar times. Full ALIGNN takes longer for the best accuracy. MegNet takes more time but predicts multiple properties. The Pareto frontier helps identify optimal choices based on your constraints. For method selection, consider your use case. For prototyping, early fusion provides easy implementation with sufficient accuracy improvement. When maximum accuracy is required and computational cost is acceptable, use ALIGNN full version. For multiple property prediction with data efficiency focus, choose MegNet multitask. When stability and risk diversification are priorities, late fusion allows using existing models with ensemble benefits. To summarize Chapter 5, early fusion concatenates composition and GNN features, achieving meaningful improvement over CGCNN alone. Late fusion provides ensemble stability through weighted averaging. ALIGNN uses line graphs to explicitly model bond angles, achieving state-of-the-art performance. MegNet enables efficient multitask learning with shared representations. Each approach offers different trade-offs between accuracy, efficiency, and practicality. In the next chapter, we'll learn practical workflows using PyTorch Geometric and the Materials Project API. We'll cover data acquisition from Materials Project's extensive crystal structure database, creating custom in-memory dataset classes, distributed training with data parallel for multi-GPU acceleration, mixed precision training for speed and memory optimization, and production deployment with Fast API. See you in Chapter 6.